So, welcome to the lab practical for computational chemistry for experimentalists, module number 12, discussing NMR spectroscopy. In this lab practical, we're going to compute the NMR spectrum of methanol in CDCl3, and we're going to compare the results to experiment. Now, I'm logged into a remote desktop connection. I've got Gauss view up and running. I've got all of my environment variables set, so I can run this calculation. Now, the first step in predicting an NMR spectrum is to get a good geometry. NMR chemical shieldings turn out to be very sensitive to the positions of the nuclei, so optimizing the geometry is really important. So we're going to create a new molecule, and we're going to model methanol, and we're going to try and replicate the experimental spectrum of methanol diluted in CDCl3. We're going to set up a calculation, start with the geometry optimization. We're going to use DFT, and in my case, I'm going to use a relatively small basis set, 631. Actually, we're just going to do 631G. You would probably want a somewhat larger basis set if you wanted to do production calculations, but to make this run quickly, I'm going to stick with a small basis set. We're going to do a solvent model. We're going to try and model everything in chloroform as a decent model for CDCl3. Optimize methanol. Now, as this calculation is running, I want to mention one thing. When we do a calculation on an isolated molecule, we compute what's called the absolute chemical shielding, which involves the second derivative of the energy of the molecule with respect to an applied magnetic field and a magnetic moment on the nucleus. Remember that experimentally, NMR measures the energy that it takes to flip a nuclear spin from spin up, spin aligned to spin anti-aligned with an applied magnetic field. So you need both a spin on a nucleus and an applied magnetic field. All right, we're going to open our optimized geometry. Looks pretty reasonable. And now we're going to compute. Now we're going to compute the NMR spectrum. We're going to turn the job type tab to NMR. We're going to use the same basis set. We're going to use the same solvent molecule, same DFT method, and we're going to use the default gauge including atomic orbitals method. I discussed briefly in the lab handout, the theory handout, that there's an extra degree of freedom when you try and model both electric and magnetic fields using both scalar and vector potentials. This is an old electrostatics, electrodynamics issue that predates quantum mechanics, so we're going to deal with it here within this particular method. And for our case where we could compute spin-spin couplings, I'm going to leave that out because it takes extra time. But if you wanted to know spin-spin couplings, you could do it that way. So I'm going to submit this job. With a new name. And let the calculation run. Now I'm going to start putting together in a blank workbook my absolute chemical shieldings. All right, so here's my log file. And I can close the input file right now. The geometry is the same as in the input file, and I can go to Gauss view and I can look at the self-consistent field gauge including atomic orbital magnetic shielding, and you see we have absolute shieldings in what it's calling parts per million, but that's not really quite right because here there's no reference. Now Gauss view has sort of a way to look at the reference chemical shielding with respect to a DFT calculation, but we're going to leave that out for now. And so the important part is that we have two different sets of peaks. There's the reference and two different sets of peaks, one for the CH3s and one for the hydrogen. These are labeled with numbers. If I view atom labels, I can see that, not surprisingly, atoms 2, 3, and 4 are the hydrogens on the methyl group. Atom 6 is the hydrogen on the OH group. The better way to look at this is to actually look at the output file. So now I'm at the bottom of the output file from this NMR calculation, and I scroll up a little bit and I get the calculating GIO nuclear magnetic shielding tensors. And what I need are these isotropic magnetic shielding tensors in parts per million. So for the hydrogens, I have atoms 2, 3, and 4. The isotropic is all about 29.15. I'm not going to worry about the small differences between these. In this isolated conformation, these two hydrogens, 3 and 4, are slightly different than hydrogen number 2, but in a real experiment in solution, rotation about the carbon-oxygen bond would average all of these together. If I wanted to be very careful, I could take the average of atoms 2, 3, and 4, but instead I'm just going to copy atom number 3 and use that as representative. So we're going to have CH3, and then we're going to be the OH hydrogen, 32. And these are all in parts per million. Proton, absolute shielding. And now if I really want to be careful, what I need to do is compute the absolute chemical shielding of my reference nucleus. So when you do this, I would recommend that you do a new calculation on your reference system. In our case, say we're doing an experiment where the hydrogen chemical shifts are referenced to tetramethylsilane, I would need to do a calculation on tetramethylsilane. I'd need to do the same thing as before, do a geometry optimization. Now, in our case, we can assume that I'm going to do a geometry optimization. I'm going to skip the optimization step to save time, but you would need to do that in general. I'm going to use the same method as before. DFT 6311G plus, actually, I think we did just 631G. Now I need to double check sure that I double check and use exactly the same method and exactly the same basis set as before. B3 lip, 631G, solvent, chloroform. So B3 lip, 631G, solvent, default, and chloroform. Okay. Okay, tetramethylsilane, NMR. Now this calculation will run for a little while, but I'll get, it's not perfect because I didn't optimize the geometry, but I'll get a predicted NMR shielding of all 12 protons in this molecule. And I'll just take the average of them. Actually, they should all be the same, but I can take the average because I'm not going to have perfect symmetry necessarily. And then I'll use that as my reference value right here. So relative shielding. This is going to be the absolute shielding minus the absolute shielding of the reference nucleus. The calculation is still running. It takes a little while to do these diagonalizations. Just for reference, I'm going to take a look NMR spectrum. And what do I see? I see I have a peak at 3. This is in neat methanol. This lower temperature proton exchange is slow, spin coupling is resolved. I have one at about 3 parts per million, and I have one at about 5 parts per million. Now our calculation is finished. We have a general idea of what's going on here. There's our log file. We'll take a look at the stream, the output file, and we look at the isotropic chemical shieldings of the protons, all about 33.56. There's a little bit of variation due to not being perfect, but do this. And there we go. I think the signs are off here. Because of the sign convention. And we find, okay, 0.7, 4.4. So experiment. The protons are at about 4.8, and this is about 3.3. So because we've ignored hydrogen bonding to the solvent, our relative shielding of the OH proton is not quite matching experiment. But this is a good start. So we could always do the tricks that we already know for solvation. We could do an explicit solvent. We could have our methanol as a hydrogen bond donor to a single molecule of chloroform if we wanted to capture some of the effects of hydrogen bonding to solvent. And that would probably give us a better answer for the proton. But overall, this is the basic idea. This is how we do this. The computations are going to be fairly simple. Now, what I've given you in the homework is something a little more complicated, where you're going to do something similar to what we did with the infrared and Raman spectra. You're going to look at a conformational equilibrium in solution. You're going to make predictions about that conformational equilibrium, and you're going to test those predictions by predicting what is the NMR spectrum that I would expect to see, and then what happens when I compare that to experiment, and can I use a fit to experiment of the NMR spectra of 2 different conformers? Can I fit that to experiment to give me a predicted equilibrium constant? So that's the basics of predicting NMR. There's all kinds of things that you could look at, looking at more complicated coupling with spin. You could look at spin-spin coupling. You could look at coupling with electronic spin. There's all kinds of interesting, complicated things that you can do. But this is the basics, and this is enough to get you started. So I hope you enjoy.